Now, we shall discuss on chapter 6. The title of this chapter 6 is some fundamental theorems of bounded linear operators. We know that in a metric space, a mapping is said to be an open mapping if it maps every open sets into open sets of another metric space. Also, we know that neither all open mappings are continuous or all continuous mappings are open mappings. So, in this module we shall discuss on a very fundamental theorem called open mapping theorem, and it has a great importance. So, in this theorem we learned that every linear mapping is an open mapping under which conditions. So, in this regard the completeness property of a nonlinear space are assumed. So, let us have a discuss on open mapping theorem. We now start with module 1 of chapter 6. The module 1 starts with the theorem open mapping theorem. Before going to the statement of the open mapping theorem, we would like to say something. Open mapping theorem is one of the basic theorems for the development of the general theory of nonlinear spaces. The theorem gives conditions under which a linear mapping is open. In this theorem, we begin to appreciate the importance of the completeness condition for nonlinear spaces. A mapping of a metric space into another metric space is said to be open map if it maps open sets to open sets. Neither all continuous mappings are open nor all open mappings are continuous. It has already been told by me. The statement of open mapping theorem is this, that is, let capital X and capital Y be two Banach spaces, that means a complete nonlinear spaces, and let T belongs to BD LXY means the collection of all bounded linear operators from x to y be surjective. That is, let capital X and Y be two complete nonlinear spaces and let T is a bounded linear operator from x to y which is onto, then T is an open mapping. Now, we are going to proof of this theorem. The proof of the above theorem shall rest on following lemma, which we prove first. The lemma is this: let capital T x to y be a bounded linear operator which is onto, and let S naught is equal to S1 theta x. That means, the open unit ball of x centered at 0 vector with radius 1. Then T S naught contains an open ball centered at 0 vector in y. That is, T S naught contains an open ball centered at theta y in y, where theta y is the 0 vector in y. We complete the proof in 3 steps as consideration and given below. Number 1, T S naught bar contains an open sphere centered at 0 vector in y. That is, the closure of T S naught contains an open sphere centered at 0 vector in capital Y. If Sn is equal to open ball S 1 by 2 to the power n theta x, that means, the open ball centered at 0 vector of x with radius 1 by 2 to the power n taken as Sn, then the closure of T Sn shall contain an open sphere centered at 0 vector in y. That is, T Sn bar shall contain an open sphere centered at theta y in capital Y. And number 3, T S naught contains an open ball centered at 0 vector in capital Y. The proof is given below. Let Sk is equal to S theta x comma 2 to the power minus k, that is, the open ball centered at 0 vector of x with radius 2 to the power minus k. That means this is a set consisting of all elements in X such that norm of X less than 2 to the power minus k for k is equal to 1, 2 and so on. Let X belonging to capital X and k is equal to third bracket 2 norm of X plus 1, where third bracket 2 norm of X denote the integral part of third bracket 2 into norm of X. So, k to the power minus x belongs to S1, that is the unit ball centered at 0 vector with radius 1. Since norm of k inverse x is equal to k inverse norm of x, which is equal to norm of x divided by third bracket 2 into norm of x plus 1, which is less than half. By easy calculation we can see it. So, x belongs to small k into S1, hence capital X is equal to union k equal to 1 to infinity k into S1. So, capital Y is equal to T of capital X as T is surjective, and Tx is equal to union k equal to 1 to infinity k T S1, which is again equal to k equal to 1 to infinity k T S1 bar. Taking closer does not add more points to union k equal to 1 to infinity small k T S1 is equal to y. That is why Tx is equal to union k equal to 1 to infinity k T S1 is equal to union k equal to 1 to infinity k T S1 bar. Since y is complete by Bayes category theorem, what is the statement of Bayes category theorem? That is, every complete metric space is a set of second category. So, as y is complete by Bayes category theorem, it is of second category. So, there exists a set say k T S1 which is not nowhere dense in capital Y for some k. That is to say, k T S1 bar contains an open ball for some k. That means there exists an open ball SYR, that is the open ball centered at Y with radius r in capital Y such that SYR is a subset of TS1 bar. We shall now show that S theta y r subset of TS0 bar, that is the open ball centered at 0 vector in Y with radius r is within the closure of TS0. From equation number 1, that is SYR subset of TS1 bar, we see that SYR minus y is equal to TS1 bar minus y. So, S theta yr subset of TS1 bar minus y, that is the open ball centered at 0 vector in Y with radius r is a subset of closure of TS1 minus y, which is again within TS0 bar. In fact, let y0 belongs to TS1 bar minus y. So, y0 plus y belongs to TS1 bar. Since y belongs to TS1 bar, we find un is equal to TWN belongs to TS1, where Wn belongs to S1 such that limit n un is equal to y0 plus y, and Vn is equal to Tzn, which is again an element of TS1 where Zn belongs to S1 such that limit of n Vn is equal to y. Now, Wn minus Zn is less or equals to Wn plus Zn. This follows by triangle inequality in norm axiom 3, which is again less than half plus half is equal to 1. Hence, Wn minus Zn belongs to S0. Now, by linearity of T, we see that
Twn minus Zn is equal to Twn minus Tzn is equal to Un minus Vn, because we have assumed that Twn is equal to Un and Tzn is equal to Vn. So, Un minus Vn goes to y0 as n tends to infinity. So, y naught belongs to Ts naught bar. We shall now prove the part B. Take Sn is equal to open ball centered at 0 vector in x with radius 2 to the power minus, that is s theta x 2 to the power minus n is considered as Sn, which is again a subset of x. Since T is linear, Tsn bar is equal to 2 to the power minus n Ts naught bar. By routine verification, one can obtain s theta y comma r 2 to the power minus n subset of Tsn bar, which is named as equation number 2. So, B is proved, what we wanted to prove. So, for the last part, the proof of C looks like this. So, we shall show finally that the open ball centered at y with radius r by 2, that is s theta y comma r by 2 is within Ts naught bar for some r greater than 0. For this, let us assume that Z belongs to open ball centered at y with radius r by 2, that is Z is taken from s theta y comma r by 2. So, by 2 we get Z belongs to Ts1 bar. So, we find norm of Z minus Z1 is less than r by 4. So, by 2 Z minus Z1 belongs to the open ball centered at 0 vector in y with radius r by 4, that is Z minus Z1 belongs to s theta y comma r by 4, which is again a subset of Ts2 bar, that is the closure of Ts2. Hence, there exists Z2 belongs to Ts2 such that norm of Z minus Z1 minus Z2, which is again a less than r by 2 cube. Continuing this process, we find norm of Z minus k equal to 1 to n Zk is strictly less than r by 2 to the power n plus 1, which is equation number 3, where Zk belongs to Tsk. So, Zk is equal to capital T xk for some xk belongs to capital Sk. Thus, from 3 we get Z is equal to k equal to 1 to infinity Txk. Since norm of xk is strictly less than 2 to the power minus k, we have sigma k equal to 1 to infinity norm of xk less than 1. So, k equal to 1 to infinity xk is convergent. Let sigma k equal to 1 to infinity xk is equal to x, which is again an element of x. So, norm of x is equal to norm sigma k equal to 1 to infinity xk, which is again less or equals to k equal to 1 to infinity norm of xk, which is again less than 1. So, it follows that x belongs to s naught, which is equal to s theta x comma 1, that is the open ball centered at 0 vector in x with radius 1. Hence, by continuity of t, we get Tx is equal to T of sigma k equal to 1 to infinity xk, which is equal to T limit of n sigma k equal to 1 to n xk. So, by linearity of t, we get limit of n sigma k equal to 1 to n T xk, that is T of limit n sigma k equal to 1 to n xk is equal to limit n sigma k equal to 1 to n T xk, which is again equal to sigma k equal to 1 to infinity T xk, and which is equal to z. So, z belongs to s theta y comma r by 2, that is the open ball centered at 0 vector with radius r by 2. This implies that z belongs to Ts0, as z is equal to Tx, which is an element of Ts0. We say that S theta y r by 2 subset of Ts0, that is S theta y comma r by 2 subset of Ts0, that is S theta y r1 subset of Ts0, where r1 is equal to r by 2 greater than 0. This implies the open ball centered at 0 vector in y with radius r1 is within the set Ts0. We shall now prove that T is an open mapping. For this, we shall show that T maps every open set in X to an open set in Y. So, let us take G be an open set in X. We show that Tg is open in Y. By showing that every Y belongs to Tg, there exists an open ball centered at Y which lies entirely within Tg. That means we have to prove that Y is an interior point of Tg. Let Y belongs to Tg. So, there exists X belongs to capital G such that Y is equal to Tx. As G is open in X, there is an open ball centered at X which lies entirely in G. Hence, G minus X contains an open ball centered at theta x, which is again an element of capital X. Let radius of open ball be equal to r, which is positive. Take r1 is equal to 1 by r, then r is equal to 1 by r1, and r1 into G minus x contains the open unit ball centered at 0 vector belonging to capital X. Now, by previous lemma, we say that T of r1 G minus x is equal to r1 Tg minus Tx by property of linearity of T. So, r1 Tg minus Tx contains an open ball centered at 0 vector in X, so does Tg minus Tx. Hence, Tg contains an open ball centered at y is equal to Tx. As y belongs to Tg is arbitrary, it follows that Tg is open in y. So, we get a corollary in respect of the open mapping theorem. If capital X and capital Y are Banach spaces and T belongs to BDLXY is bijective, that means if T is a bounded linear operator from X to Y which is bijective, then T inverse is again a bounded linear operator from Y to X. Since Tx to Y is bijective, its inverse T inverse exists, and it can be easily seen that it is linear. Further, under the hypothesis and by open mapping theorem, it follows that Tg is open set in Y whenever G is open in X. Also note that inverse of T inverse of G is equal to Tg. This shows that T inverse is continuous and hence bounded. This result is also known as Banach inverse mapping theorem.
Just now we have proved a theorem, that is open mapping theorem. The statement of the open mapping theorem is this, that if X and Y are two Banach spaces over the same field of scalars and T belongs to BDLXY which is surjective, that is if T is a bounded linear operator from X to Y which is onto, then T is an open mapping. In this regard, we have got a corollary, that is if X and Y are two Banach spaces over the same field of scalars and if T belongs to BDLXY be bijective, then T inverse is again a bounded linear operator from Y to X. So, in general we get a corollary. Let X and Y be two Banach spaces over the same field of scalars and T belongs to BDLXY be surjective, then T is a topological isomorphism between X and Y. Thus, in this regard we get another two results, that is if X and Y be two Banach spaces and T X to Y be a bounded linear operator, if T is bijective, then T is a topological isomorphism between X and Y. We get another result,
let x1 is equal to x is equipped with norm 1 and capital X2 is equal to x equipped with norm 2 be two Banach spaces with the same underlying linear space capital X. Suppose that there exists a constant k greater than 0 such that norm of x1 is less or equals to k into norm of x2 for all x belongs to x, then norm 1 and norm 2 are equivalent norms. Now, we are going to prove of this result. Consider the identity operator I from x2 to x1, that is Ix is equal to x for all x belongs to capital X. Clearly, identity operator is a bijective linear operator. Also, under this hypothesis, I is a bounded linear mapping. So, I inverse x1 to x2 is a bounded linear operator. Consequently, by the definition of boundedness, there exists a constant k1 greater than 0 such that norm of I inverse x2 is less or equals to k1 into norm of x1 for all x belonging to capital X, and which implies that norm of x2 is less or equals to k1 into norm of x1 for all x belongs to capital X. This together with the hypothesis gives k inverse norm of x2 less or equals to norm of x1 less or equals to k into norm of x2 for all x belonging to capital X. Hence, norm 1 and norm 2 are equivalent norms on capital X. Consider the Banach space capital X C01 with norm 1, where norm 1 is defined by norm of f1 is equal to sup of modulus of ft, where 0 less or equals to t less or equals to 1. Also consider a nonlinear space capital Y which is equal to C01 equipped with norm 2, where norm 2 is defined by norm of f2 is equal to integration 0 to 1 modulus of ft dt. Then the identity operator I x to y is bounded. Since norm 2 of if is equal to norm of f2 less or equals to norm f1 for all f belonging to capital X. Also the operator, that is the identity operator, being bijective, we can consider its inverse mapping I inverse mapping from y to x is again linear. We now claim that I inverse y to x is not bounded, that is not continuous. Let sequence Fn be a sequence in C01 where Fnt is equal to 1 minus Nt, where 0 less or equals to t less or equals to 1 by n, and Fnt equal to 0 where 1 by n is strictly less than t less or equals to 1. Note that Fn tends to 0 as n tends to infinity in y, but I inverse Fn with respect to norm 1 is equal to norm of Fn1, which is equal to supremum of mod of Fnt, where 0 less or equals to t less or equals to 1, which is again equal to 1, which implies that I inverse Fn does not tends to 0 function in x. This shows that I inverse is not continuous and hence I is not open mapping, that is the identity operator is not an open mapping.
See what we have learnt in this statement of the open mapping theorem. We have assumed the completeness property of the nonlinear spaces. So, the underlying spaces must be taken as Banach spaces. So, completeness property cannot be avoided from the statement of the open mapping theorem. For this already we have cited an example that has already been discussed, and with this we come to an end of this module 1 of this chapter 6.